Yeah, can you make a full screen or play it? Yeah. That looks
And
good.
you can see the pointer.
Yeah, I see the pointer. The slides looks great. So
right,
let me introduce you. So next speaker is Matt Lewandowski. He's going to tell us about factoring inflation, a double copy approach to Volkov-Akulov goldstinos in dynamic spacetime. So please go ahead.
All right, thanks a lot to the organizers and for everyone for coming and watching the talk. So yeah, I'm going to talk about a double copy approach to inflation and supergravity. And this is work that should be coming out soon with JJ, Nick, and Aslan at Northwestern. So Nick and Aslan are two great grad students who have done a lot of great work here. So let me get started with the motivation. So we're going to start by noticing that there are some interesting models of inflation in supergravity that are called alpha attractors, which describe some of the observables we have in inflation. These are based off of what are called nilpotent superfields in supergravity. Those are known to be kind of equivalent to what are called Volkov-Akulov fermions. So the part where it starts to get interesting for this conference is that those Volkov-Akulov fermions are known to be double copies of a pion with n equals 4 super Yang mills. And so that's in flat space. Now, to connect back up to our inflationary scenario, we want to couple these Volkov-Akulov fermions to gravity because they're embedded in a supergravity model. And so what we really would like is to have a double copy description of these Volkov-Akulov fermions coupled to gravity. And that's what we're going to get at here. So this is interesting for a few different reasons, but for this conference, I mean, it's a new gravitational context to be looking at the double copy. You know, we have gravitational waves, things like that. And so inflation now is a new kind of playground, hopefully, where double copy will have a lot to say. So, okay, so I'm going to do a lightning review of inflation and supergravity here. So inflation, it's gravity coupled to a scalar field in a standard way. This scalar field gets a background time-dependent value, which makes the metric quasi-de Sitter. So you have exponential expansion. Now there are perturbations around this solution. There's scalar perturbations called zeta, H perturbation, Hij perturbations, which are tensor perturbations. In cosmology, we're always interested in kind of correlation functions of our perturbations. And so 2-point function defines for us the power spectra. The power spectra of the scalars is almost scale invariant. It means it almost goes like 1 over k cubed. There's a small scale dependence, ns minus 1. This ns is one of the things that we can measure from inflation. And then the tensor perturbations are also scale invariant, have some other amplitude. And so R is the ratio of the power spectra of the tensors to the scalars. And that's another thing that we can measure from the CMB to start looking at inflation. Now, these alpha attractor models are interesting because they seem to fit the data well. So what are they? They're essentially very similar kind of setup of inflation, except you have a modified kinetic term for the scalar field, which through a field redefinition, you can look at as a kind of a specific type of potential that you have, which are these tanh potentials that I've drawn out here. And so for large fields, you have this kind of very slow roll regime on the edges of these potentials. The interesting part for the cosmological measurements that we have is that these predictions of these alpha attractor models are essentially independent of the actual V that you pick. And so there are kind of robust predictions for what NS and R should be in these models. And so if we look at a very confusing and complicated plot here, which I'll describe, we can see why these models are interesting. So first, these are constraints on NS and R. The green blob is the Planck constraints, which are a couple years old. And the blue blob is newer bicep constraints, which measure tensor modes in the CMB. So you can see that NS and R are kind of constrained to be lying around, around here. Now these models, these other lines, it gets very confusing. So I'm just gonna do one example here, which is phi squared. Let's imagine you had just standard inflation with m squared phi squared. Then this red line here would be essentially where you would predict NS and R to be. And that's way off from where the constraints are. So that model should not, it doesn't fit. However, when you start with that, but then you do this alpha tractor models, actually the predictions kind of come down with these yellow lines as you tune this parameter alpha to be small. And in fact, with many other potentials, you kind of have this tuning with alpha small, all approaching the same area on this plot. And so all these alpha tractor models essentially kind of unify in this region, which seems to fit well the data. So that's why this are phenomenologically interesting. But in terms of model building, you might ask, right, like, can I actually have these alpha attractor models in supergravity? The reason that might be difficult is because when you start doing inflation, you have many extra scalars and you have to stabilize potentials, et cetera. And that can become kind of confusing. But there's another technique called Milpa and superfields which help. And I'm going to very quickly just say what happens. You introduce some fields into your supergravity model, an inflaton field and a goldstino field. You impose some kind of constraints with Lagrange multipliers, s squared equals 0, s times this imaginary part of phi 0, etc. And this helps because it eliminates all these extra scalars that you would have around. And so what you're left with is the inflaton phi that you want and some extra goldstino field G here. And in these models, you can, once you do that, you can essentially get the inflaton potential that you want. And why is that interesting for amplitudes? Well, it turns out that when you do that, the action for the goldstinos has a very particular form, and it's called the Volkov-Akulov action. Now, the Volkov-Akulov fermions are known to have a double copy in flat space. So that's when your ears kind of perk up. This should be interesting. You want to extend it to gravity. And so what we would like to see is to describe this supergravity inflation models, we need Volkov-Akulov coupled to gravity. And so we're going to approach that in a double copy way. Okay, so, and then for the cosmology people, a very, very quick double copy comments. So we start with the simplest thing, which is Yang-Mills, which is an SUN theory. We have a gauge field A, the generator is T. We get a very specific form of the action, which has, the FABCs or color factors give us all the interactions of these gauge fields. It means that we can write the amplitudes in a very kind of clean, particular way, where we write in a canonical way, the way that all these color factors enter, and then the coefficients of them, this is like a color basis, and the coefficients are called partial amplitudes. Now for double copy, which we're going to get to, it's interesting to write the amplitude in a slightly different way. So here I'm going to write the tree level amplitudes in Yang-Mills as a function of K, the external momenta, epsilon, the external polarizations, and little a, the external color factors. So this is a sum over trivalent graphs, and we can break each term into this kind of structure. So the C are called color factors. They depend just on the external color. The N are called numerator factors or kinematic factors. They depend on the external kinematics, momentum and polarizations. And the Ds are just the propagators. Now, because we're in a gauge theory, we have these F satisfy Jacobi identities, which is inherited again by these Cs. So at 4 points, the amplitude is just 3 different graphs, which I drew here, S, T, and U channels. And the important thing is that these color factors, CS, CT, and CU, satisfy a Jacobi identity. Okay, now I wrote the amplitude here at 4 points. The N factors, the numerators, the kinematic numerators, they're not unique. So the color is fixed by the interactions. but the kinematic factors are not unique because, for example, I could just do a gauge transformation and shuffle contributions between different diagrams. However, if there is a choice of kind of generalized gauge transformation, which brings you to these numerator factors satisfying the same relationships that the color factors satisfy, we call that color kinematics. And that is when you can start doing very interesting stuff with double copy. So in Yang-Mills, if you simply replace one of the color factors in the amplitude with the color dual kinematic numerators, this gives you a special kind of, it gives you an amplitude. It gives you a special amplitude because it inherits linearized diffeomorphisms from the gauge invariance of Yang-Mills. And you can basically show that the states that you end up with when you do this double copy are essentially in the direct product of the Yang-Mills states that you put on the external legs. And so this gives you gravitational amplitude. And the states that you get in the gravitational theory are dictated by the states that you put into the, that are coming in from Yang-Mills. It's a spin 2 amplitude, it inherits linearized diffeomorphisms. And so these are, but it can have other states other than just graviton. And this is the standard gravitational double copy. And so just as a final comment, the color kinematics that I mentioned about these numerators satisfying certain relationships are also called, at the level of the partial amplitudes, BCJ relations. So they're extra relationships that partial amplitudes satisfy. Okay, so like I said before, we know that Volkov-Akulov, which is also with DBI part, but not details not super important there, but these Volkov-Akulov theories are already known to be double copies in flat space, but now we want to add gravity. Well, we just saw how to do that with Yang-Mills, and so you can kind of guess that what we want to do is something like this. So we want to, what we're going to, our approach is going to be to consider, you know, this nonlinear sigma model pion, but plus a Yang-Mills sector. So we want pions coupled to Yang-Mills and then double copy that with, for example, n=4 super Yang-Mills. The kind of table of different states that you can get is something like this. And so when we cross, you know, the gluons on one side with gluons on the other, we get our gravity theory that I just told you about. And then when you cross the other states, you get a bunch of other stuff. In particular, when you cross the nonlinear sigma model from the left-hand side with the fermions in n=4, you get the Volkov-Akulov fermions. And so this is a theory which has Volkov-Akulov fermions coupled to gravity. And so, and it, you know, is our proposal as a double copy here. And so that's what we hope to be useful for inflation. And so super Yang-Mills amplitudes and numerators are very well understood and known to be color dual. And so what we need, what we want for this project is color dual numerators for pi plus Yang-Mills. And that's going to be our first kind of, our new kind of addition to this story here. And so that's what I'm going to tell you about now. Okay, so pions coupled to glue. So what do we want in this theory? So of course we want some SUN gauge theory, like we had before with Yang-Mills, but now we want to have matter in the adjoint. We'll do for now. We imagine there's two couplings for this. There's the gauge coupling G, and then there's the self-coupling of the pions lambda. And so we're gonna have a bunch of new diagrams like this. The kinds of diagrams I'll draw here, the squiggles are the gluons and the solid lines are the scalars. And we want to explicitly construct these amplitudes in a way that gives us numerators that are already color dual so that we can use directly the double copy. There's many interesting works about scalars and Yang-Mills. Most of them essentially either scalars or Yang-Mills that have interesting properties. Here, we want the pion to be coupled to Yang-Mills, which is, a lot of the time that's not what you want, because the reason you have pions is because you wanted to look at you wanted to basically integrate out or decouple the longitudinal mode of the gauge theory. But in this case, we want massive gauge theory coupled to this massless gauge theory coupled to these pions, just because that's what the double copy seems to want to get the states that we want for inflation. Okay, so how could you do this? Well, you could start by just writing down an action, deriving the Feynman rules, computing the partial amplitudes, and things like that. Or you could take a more modern approach, which is what we do here, which is basically just constructing the amplitudes from mass dimension, symmetries, creating some ansatz for the kinematics, imposing BCJ relations directly, and doing a bootstrap to go to higher orders. And then we kind of worry about which action it matches sometime later on. And the important part here is that you just impose color kinematics directly on the ansatz. So you get color dual numerators. So for example, if you wanted to do an action, you might start with something that looks like this. You start with a gauge theory coupled to essentially some kind of covariantized version of nonlinear sigma model, where you just add in this covariant derivative for the interactions of the gluons with the pions, and then you just compute all the Feynman rules and amplitudes, etc. But the question is, there's no necessarily any reason that the amplitudes have to satisfy BCJ relations. And then, if they don't, then the numerators are not color dual, and that is not good for double copy. And that would mean that you have to throw this kind of whole hope of easily describing these fields out the window. And so we want to just construct them directly, from the ground up, to give us the best chance of getting something useful. All right, so let's start on that little journey. So we start with 3-point functions that we want in the theory. This is kind of always what you do. You start with the 3-point functions. You can again give an ansatz for what using mass dimension and behavior under switching the legs from the color factors. Give an ansatz for what you think the kinematic factors, or give an ansatz for what the kinematic factors could be. Some general expansion that has 1 power of k, and the 3 polarizations of the external fields. For the Yang-Mills side, and just write down the most general thing. Then you start imposing your various constraints, and it actually fixes these amplitudes to be in this form. So they're, in this sense, unique. So you just end up with the correct 3-point functions from symmetry. Then you kind of go up to 4 points, right? So for example, looking at pi on 4-point function, all these diagrams have the same kind of topology. So I can again give an ansatz for the kinematics of this diagram. Now I have a new constraint to impose, which are the cuts, right? I do a cut in the channel, and then it has to factorize into 2 products of the 3-point functions I wrote earlier. And once you constrain what NS is, you can just directly impose, these other 2 diagrams are just determined by shuffling around the external legs, right? They're all the same, so it's just relabeling the diagram. But now we have this contact term because we want to have self-interactions of this field, and so that's very easy to do. You basically it's going to have the correct kind of FABCs that factor out of the amplitude that match diagrams like this. And since it doesn't have a propagator, you basically just have to multiply and divide by a propagator. But this still fits into the equation for the double copy as the numerator. And this is what you get as the unique numerators for this for these amplitudes. Okay, so now we have something slightly more interesting, which is now we include gauge field. And now we have two different topologies, right? We have one where there's a gauge field in the propagator, and one where there's a scalar. Now, on the right-hand side, let's say I do my cuts and construction and impose symmetries on, say, this diagram. Then the diagram over here to the right is just a relabeling of this one. And so if I set NT prime equal to just the difference of these two, I automatically get numerators which satisfy color kinematics. And that's how, that's basically, in a way, how you're able to construct directly color dual numerators. You just immediately impose it as soon as you can. Okay, this is great so far, we're on the way, but so this is not really a new story so far. We've just have the contact interaction plus all G squared contributions at Fourpoint, which are essentially equivalent to Yang Mills or simple scalar, which is stuff that people have already looked at. But now we come to where really new stuff is entering, which is at 5 points. And so the as we go to higher multiplicity, the first kind of diagram which becomes new and yeah, just needs some more interesting explanation is this 5-point diagram here. We have 4 pions and a vector. So this is what we call the master graph. You get other graphs by doing Jacobi relations, which are kind of like these operations on the legs, which look something like this. So you just give a kinematic ansatz to this diagram, start imposing constraints like BCJ, or yeah, so you start with just 45. You write down all the possible kinematic terms that you can, and at least with momentum conservation, that gives you 45 terms in an expansion. Then you start imposing symmetry and Jacobi identities. Jacobi is basically this in parentheses where I have this master diagram, but I can use Jacobi to switch around the legs in some way and then rewrite it back in terms of the master diagram. That gives me a constraint on relabelings of the master diagram, basically. That constrains 33 more parameters. Then you have a cut, which cuts you down to 4-point pion amplitude times the 3-point amplitude. That constrains 8 more parameters. And then gauge invariance constrains one last one, because we have one gauge boson on the external leg. And then you're left with 3 parameters. And then you could just check by computing some physical observable that all those 3 parameters just drop out. They're just generalized gauge parameters. When you add up all the diagrams, all the partial amplitudes to form the full amplitude, these all drop out. And so said another way, they can all be eliminated by choosing a certain gauge. So this essentially uniquely fixes this 5-point numerators by cutting down to 4 pion amplitudes. So this is good. Now we have color dual numerators at 5-point that we can use in a double copy.
Matt, you have 5 minutes left, including questions.
Okay, great. So as a kind of final end to the story, we can also go to loop level. And so can we use these 4-point amplitudes that we have through unitarity to write down some loop amplitudes? So the way that this works very quickly is, you have some kind of a few different types of loop diagrams. When you do your cuts to use generalized unitarity to construct the loops from cuts, you can see in this blue part here in each diagram that the various loop diagrams are related by doing a Jacobi identity on this blue part. Now that is just exactly the 4-point Jacobi identities numerators that we were using before. So in the end, what this means is that the loop diagram itself can also be written in a kind of double copy form. where you integrate over the loop momenta, but this numerator, this kind of blue numerator here, they satisfy Jacobi, and so then it allows you to then construct a gravitational amplitude by just this simple formula, replacing the color with the kinematics. Okay, so I'll conclude here and give a quick look forward. So the main point is that we construct these color dual numerators from the ground up for pions coupled to Yang mills. And this is relevant and potentially, phenomenologically relevant and super interesting because it's related to inflation through these Volkov-Akulov fermions coupled to gravity. Now, there's a lot of interesting ways to go here. For example, we just described the lowest order scattering of these Volkov-Akulov fermions, but of course, if we want real inflation, we need a potential, right? And so that's presumably going to correspond to some higher derivative description of the double copy description of these interactions, because we want to sort of build out this potential from higher derivative operators. So that could be very interesting. Then there are other ways you can go, for example, using higher derivative operators with, for example, is including these alpha prime corrections by kind of going up in alpha prime to fill out like the abelianized open string. So that seems like something very possible. And then, from my perspective and on the cosmology side, it would be very interesting to have, it's a first step, and it would be very interesting to have something which we can kind of directly use for EFT of inflation kind of stuff, which is of potentially very, very important phenomenological interest. So I will stop there. Thank you.
Thank you very much. Thanks for a nice talk. Let's see if there's any questions from the audience or online. So there's a question from Ricardo.
Yeah, concerning the last thing you said about the effective theory of inflation, the
Yeah.
very fact that in the effective theory of inflation is like you have a medium, you don't have relativity because the frame is broken. So for instance, you have much less. For instance, the stuff about the constraint from unitarity doesn't work because you don't have, strictly speaking, asymptotic states in the medium. Any phonon can decay into anything at any energy, right? You have a phonon split into two phonons and three phonons. How do you define?
Yeah, no,
quantities?
yeah, I totally agree that this is definitely a far off thing. Like the main thing that I'm thinking is, having pions and Yang mills is in some way, constant breaking gauge invariance. So if there's a double copy way, like you get amplitudes in a gravitational theory, which would potentially seem to break Lorentz invariance, or at least some kind of diffs. And so unclear exactly how that would work, absolutely, but some ingredients seem to be there.
Okay, thanks.
Yeah.
I have a question. So I wonder if this theory that you constructed by imposing BCJ, is this the same as the usual offshore Lagrangian from pion plus gluon?
Yeah, it's not necessarily obvious. Like I said, we construct these things, and it's possible that the actual action will have some more complicated internal states, right? And we don't necessarily know that at this point.
Because the reason I ask is that the usual action comes from massive Yang mills in the high energy limit, but as other work shows that these massive Yang mills, they don't emit the BCJ presentation. So I wonder if these two things are actually the same or not.
Yeah, I don't know exactly, but that is interesting, and yeah, maybe we can talk about that offline. Yeah, because it seems interesting.
Thanks.
Yeah.
All right. I think unless there's any more questions, I think we should probably round up here the first morning session because we're a bit behind schedule. So let's thank Matt again.